Um, so I have to admit, I have a little bit of an imposter syndrome today talking at the ML seminar because I definitely view myself more as a consumer of machine learning than a researcher. I'd like to talk today about some of the issues that we've hit in trying to do things that I consider to be data analytics or computer graphics like applications. And we've just started to build our own tooling to help us with that. So that's sort of the motivation. And maybe just to give you a few examples of some of the stuff that we've done, some of you may remember that I like tennis. I played tennis at CMU. I still like to watch a lot of tennis. And some of you may remember this fairly epic match between Federer and Djokovic. It was like a 5-set match in the Wimbledon final. Okay, so here's Djokovic and Federer playing. Hopefully you can see this video. Let me know if you can't. And so the little sleight of hand that I'm performing here is that this is not actually a Wimbledon video. This is a fake video that my students created, where we have basically said we want the ball to go to these places, and we synthesize the video to match. So what you're seeing here is completely computer graphics. And just to give you a little bit more evidence that that's true, here's a version of it where we make the players hit to the ball to the red dot, and then return to the appropriate position on the court given by the blue dot. Okay, so this is an example of something we've created just by analyzing broadcast Wimbledon footage. And in this work, the annotations, the actual labeling of some of the more detailed stuff was done by hand. And by hand, I mean by me late at night. And some of this is quite subtle. So it would, you sort of falls under the fine-grained human action recognition category. Like, for example, creating these outputs requires the system to have a database that's annotated at fine scale of the exact contact frame where, for example, Roger Federer hits the ball, as well as differentiating between shot types. So in this case, this is a topspin backhand from Federer. And in this case here, this is a slice backhand from Federer. So, for those of you that don't play tennis, this might look very, very similar. To me, I can definitely see the difference, but it's been pretty hard to get a computer to tell the difference between those two. So that's like the type of stuff that, man, if we could just annotate video a little bit more accurately, a little bit more rapidly, we're just really excited about the computer graphics applications that we could create. Okay, another example is with Manish Agrawala and a journalist named Geraldine Moriba. We have worked with the Internet Archive to obtain access. So every day we get video plus transcripts of Fox, MSNBC, and CNN. And it's available on the public right now at this URL. Feel free to browse it. And so what we're doing is not only do we expose a friendly little interface for transcript analysis, we also expose an interface that reports out on the results of face detection and face identification on all of this data. So we're hoping this will be broadly useful to folks that are interested in studying the media. Like, here's an example graph that I made a couple weeks ago now, where this is the screen time of various 2020 Democratic presidential candidates throughout the major part of the primary schedule. And there's a few things that pop out if you look closely. Like, for example, the blue line was Joe Biden. And if you look all the way up until basically he pulled ahead in March 2020 and became the clear favorite, he was not the dominant screen time candidate throughout much of the heart of the primary season. Another example, in digging into the images is, and this is, fraught with a lot of caveats, but we've done some analysis of the screen time by presenting gender of individuals. And I'd like to say up front that this plot is plotting the screen time given to male presenting individuals versus female presenting individuals, where male and female presenting were determined by a model trained on data that grad students labeled. So the notion of binary gender is something that is a very complex topic. And we think that this simplistic notion is is interesting enough to still be valuable. So we were able to find that the ratio of males on screen to females on screen over the last decade in US cable TV news is about 2-to-1. And it's been relatively stable throughout the decade. And if you might be asking, well, is that, specific to a channel? If you look at all three of the channels, you see them all roughly in the right spot. Another thing that's been kind of eye-opening in analyzing the videos is the images start to give you a little bit of a story of why or interesting phenomenon going on in the presentation of cable TV news. Like, for example, using some fairly simple techniques, we pulled all the images we could find of Trayvon Martin. And with just some simple clustering, it's pretty easy to group all the images of Trayvon Martin that appear on the news by the photo. So what I'm showing you here is every row or every image is just a different frame. And every row is, as after clustering, something that we have hand verified to say, yeah, that's the same image, And if you can compute the screen time of these images, some interesting properties emerge. Like, for example, this is the image that was most commonly shown on MSNBC when Trayvon is on screen. 30% of the time, it is this image. This is the image that is most commonly shown on Fox News. And this was the image that was most commonly shown on CNN. Okay. And interestingly, the iconic hoodie photo was actually not the most frequently used photo on any of these stations. Okay. So this, I kind of misspoke earlier. This doesn't get to tell you, why these decisions were made, but it does fairly clearly suggest that different decisions are being made about how individuals are portrayed in the news. Okay, so like I said, I feel like, a bit of an imposter talking here today, because my background and my interest has always been systems and tools for helping computer graphics engineers or artists or data analysts do their job more productively. These are some examples of some papers we've written. And so when we started doing this type of work, I couldn't help but immediately start thinking, gosh, it's painful for my students, these are some of my grad students, to go from they have an idea in their head. Like, for example, in the TV news project, someone came up to us and said, we'd like to detect the screen time of masks. We'd like to see how the different stations are portraying masks differently. And you go, yeah, that should be really easy, but it's just shockingly, the latency between idea to model that you roughly trust is incredibly high, right? And for example, in the tennis project, we wanted to expand to more data, and our ability to train up a fine-grained human activity detector was just quite a struggle. And these are folks that are pretty well versed in machine learning. So the goal that we're starting to pursue, and parts of this talk are really about, we'd love some help with this because we think other people would be better at it than us, is imagine that one of these students gets an idea. They want to identify Roger Federer slice backhands. They want to find all the interviews on TV news and so on. I would like them armed with a full palette of pre-trained models, a huge corpus of unlabeled data, which is basically the only thing that I ever work with, huge corpuses of unlabeled data. And assuming that compute is free, I'd like them to get to something that they trust as quickly as possible. So this is not democratized machine learning at all. This is like make some PhD level grad students that have taken all the machine learning classes actually be able to do their work. So they need to curate data, they need to generate supervision, they need to validate, and then they need to do this 5 or 6 times a day. Okay. So what we're trying to begin pushing towards is what I like to call, ignore the interface analogy, but the primitives analogy is something that I think is apt. If I want to perform a task like in image editing, Photoshop, and we've really worked out the right set of tools. What is the palette of tools that I need to get that job done? And so what we're intellectually very interested in is what is the palette of primitives that are necessary for my students, whether it be for new training algorithms, new ways to explore data, that can make them successful in getting their job done. Again, in a time scale of idea in the morning to hopefully some model that's reasonably trustworthy in the afternoon. Okay. So are there maybe any questions about that, or if anybody wants to take me a task for that setup, this would be a good time to do so. Okay, well, let me refine it a little bit. And one of the things that sort of we found is a little bit different is most of the time when we're looking for something in real world data, the reason why we're looking for it is that it's probably interesting and relatively rare. So many of the models we wish to build are for rare objects or rare events. Okay. And so what I'd like to talk about for the next 20 minutes or so is some of the techniques that we've slowly been coming up with. Many of those techniques have been work done with Deva Ramanan here at CMU and Ravi Mullapuli, who's a CMU graduate student. So there's a lot of CMU work going on in this talk. And so I'd like to talk a little bit about training, and then I'm going to talk about some of the interfaces that we've starting to build to try and put all this together. Okay, so to get started, so I'm going to step back away from the applications and data sets that I just motivated the talk and move to a data set that we've been working on because it has some of the properties of our real world data sets, but is fully labeled and, to be honest, is accepted for evaluation in ML conferences, right? So that's iNaturalist, which is a data set collected out there in the wild. And the reason why we've been very interested in it is because it has so many fine-grained categories. So in terms of long tail recognition, it's actually been a pretty good data set for us. So without jumping ahead a little bit, we have found that the best methods for long-tailed or imbalanced classification, even something as simple as image classification on iNaturalist, fails pretty miserably in this regime. And this is something we found on our own data sets as well. So what we did is we modified iNaturalist. It's something that my students, Ravi and Faye, recently did. And we're trying to simulate, instead of the 5,000 way categorization task, we're trying to simulate something that's a little bit more like what we need to do most of the time, like n+1 way classification where n is 0 or 1. Most of the time we're looking for masks in our data set or something. So we're really interested in the small n case here. So we modified the label set, and the rest of this talk is going to talk about this modified iNaturalist, where we chose small numbers of rare categories and called those foreground. And then we merged everything else into the background. So this n number is the number of categories that we're actually trying to identify. And like I said, we're really most interested in like n is 10 or 1, but we did experiments with larger n as well. And as you see, as n gets smaller, the percentage of the data set that's background becomes increasingly dominant. So I just wanted to establish that before going forward. Any questions about the setup? Because this is a modification to a common, well-known data set. Okay, cool. So, and just to give you a sense of this data set, here's an example where on the left side, I'm showing you some positive examples of one category. All the other squares marked yellow are the background. And notice that not only are there some extremely hard negatives, look at the second column, there is an extremely large and diverse background, which throughout the literature that I'm aware of is known to cause problems in training. And so we took the latest and greatest deep training techniques for the imbalance setting. So techniques that use various forms of sample rebalancing or sample reweighting. We actually took the ones that perform best on iNaturalist, and we showed that as we decreased n, as we moved to a regime that we sort of feel is a little bit more real world, they largely fell apart. So if you look at LDAM and LWS, those are sort of the top performing imbalance classification models, at least to our knowledge. The top row here, FT, is just fine tuning on that label set. So actually not doing anything sophisticated at all actually gets you in a better place in this extreme imbalance regime. And we tried a fair number of things to get this work. So we were in the situation of, gosh, we can't even train the models in the diverse background setting. Okay. So what we're doing now, and this is a technique that that Ravi here at CMU came up with, was the main insight is if the dominant background is causing us problems, let's just get rid of it. So we started using techniques that, if you take a multitask learning perspective, seem fairly obvious. They just hadn't been used to address this extreme imbalance setting. So here's what we did, was we took a standard image classification model, which is what you have here on the left, and we said we're going to give it another task to perform at all times, which is not just predict the rare category classification task that we want to actually perform. We'll go ahead and give this system another head and ignore the block diagrams. Really what it is that second head is supposed to say, hey, look, go ahead and predict some other label set for the same iNaturalist data. So everything on the right is just another classifier that in this case is trying to predict what an ImageNet classification network would say on the iNaturalist data. So in other words, we have a multitask learning setup where the second head, the auxiliary head, is being supervised by pseudo labels, by machine generated labels. So there's no new labels being put into the system. And we found that by forcing the network to perform this harder, in some sense, image classification task of differentiating all of these categories, it actually we learn features that are far more useful for the task at hand. And then this is and one of the things we liked about it was that it was an extremely simple setup. At test time, you just remove the right-hand side of the diagram because the shared features down here, F are learned to do both of these tasks. And so a lot of people have asked us, well, wait a minute here, the ImageNet categories don't apply to iNaturalist. But in fact, they sort of do. In that what I'm showing you here is on the left side, these are actual ImageNet exemplars. And on the right side, you see the model, an ImageNet classifications model's 5 most confident predictions on iNaturalist. In a lot of these cases, you see that there's visual coherence in the labels on iNaturalist, even though these are not examples of the actual category that ImageNet was trained to do. And sometimes you have visual coherence that's just not even close to the ImageNet category, which is showing a lack of generalization of the model, but still there's coherence in what it is labeled, like this OWL example in the 4th column. Okay. So by splitting the background up, we went from a regime where the background is dominant and 98% or 99.9% in the extreme case of the background, all the way to the most, the commonly predicted auxiliary categories, only 4% of the data set. So we moved well back into the regime of balanced classification using this small sleight of hand, this roundabout. And the effects were quite surprising. It's this really little trick. You don't have to work on labeling any more of your data. And the result in the regimes that we care about down here in n equals 10 or n equals 1, where the background is most of the labeled data, we were able to gain large numbers of F1 points over a fine-tuned baseline, which actually happens to work significantly better than these other state-of-the-art techniques, which we couldn't even run down here in this low shot regime, or not low shot, but a low number of positives regime. And the choice of auxiliary task is about what you'd expect. If you can make those auxiliary categories line up with your data set, you get quite a big boost. So for example, we actually demonstrated that if you use an auxiliary task that's not anywhere like the classification task you're actually trying to perform, it can be destructive, as anybody in multitask learning would predict. And we've also found that you don't need ImageNet labels to supervise. We could actually use an ImageNet, we could just cluster ImageNet based on some pre-existing embeddings, and you just predict the cluster label, and that works almost as well as what I just told you. Now, there are a few interesting things that we have observed that we haven't been able to do the analysis to explain. So one common question that people get is what happens if you just pre-train, you pre-train on ImageNet, and then you fine tune. Well, that got us to about 25 AP points. Okay. And then folks are saying, well, what happens if you pre-train with just the auxiliary task? Try and essentially do some type of self-supervised or learning, and then fine tune based on your actual task labels. And that doesn't help at all either. And we've done pre-training using completely self-supervised techniques like, or unsupervised techniques like modern iClear, like, or SimClear like training. And the only way we've ever been able to get this to work is that if we jointly train with the auxiliary task and the task at hand, which is a little surprising to us because we have hundreds of thousands of negative labels, hundreds of thousands of noisy machine labels, and just adding in a few positives, like on the order of tens to hundreds of positives, can dramatically change what the model comes up with in these scenarios. And so I'd be interested for sure in having a little bit of help in understanding this phenomenon, because we don't see anything in the literature that can sort of help us understand what we're observing. So we like this. This is like a really simple multitask learning solution that allows us to effectively train models in a regime where we have hundreds of positives, tens of positives, and arguably tens of thousands to hundreds of thousands of negatives. So this has been very, very helpful to us. And it's a form of multitask learning. It's also a form of model distillation, because we're distilling the model from the information from that auxiliary task into the final network. Okay, so at this stage we're like, okay, we're feeling better. We can train now. We have this mechanism to train in this highly imbalanced setting. But what I just told you about still puts a label on every image, positive or negative. So it was not a low shot scenario. So a lot of the work that we're doing right now, and something I'm particularly very interested in, is addressing this bootstrapping problem of going from, I have an idea in my head, I may even have a few positive examples, like in this case, there's a few positive examples of this lizard. And I have this huge unlabeled image collection that I need to start mining to generate training data. Okay. And so, people come up to us and say, well, why don't you use the canon of label propagation or canon of active learning techniques? And in this regime, where we only have a few positives and the models that we create don't even have a well-established margin, we haven't been able to operationalize those techniques to start bootstrapping into getting models that do anything. And so I'm going to tell you about quickly here a few of the things that we are doing to get us out of this left side of the graph here, where we have a few examples of what we want. There's a massive amount of data available to us, and we just don't know how to start the flywheel of machine learning techniques to start building better and better models. Okay, so the first thing that we do is we are exploring active techniques, but we're exploring active techniques with heterogeneous collections of models. So we end up starting with very simple models, like given these 5 images, KNN is about the only thing I can do to start getting more positives. And then as we get a few more positives, we start ratcheting up to linear models, and then ultimately, hopefully to DNNs, and then that flywheel can really start turning. Okay, so the first thing that we do is our workflows are bootstrapped by the simplest models that can do anything, basically. And the next thing we do is we combine a hybrid of, we use the human to tell us about the positives, and we use the machine to tell us about the negatives. So this is work that's actively going on with Deva and students in the Vision Lab at CMU. And so this differs from the standard label propagation, where you have some sparse human labels and you propagate them everywhere. In our regimes, the positives are extremely sparse, and you can't trust any pseudo-labeling of positive examples. So we use techniques like KNN or simple linear models to surface hard negatives and likely positives for the human to verify and label. But then we can throw, like we use these models that are not very good, their precision is terrible, but their ranking of the images is good enough to say that the bottom of that ranking is clearly negatives. And those are how we flood the system with thousands upon tens of thousands of easy negatives. So we get a few hard negatives that the human looks at, we get tons of easy negatives, and that gives us a scenario where this background splitting technique can take over, because we have a system that is pretty good at training in situations of massive imbalance. So this is some work that's ongoing that we're likely about to submit. And the long story short is that we are trying to bootstrap from a very small number of category images. And so if you look at the left side of the graph, you'll see like we're starting with about 50 labeled images and less than that in terms of positives. And all of the non-red lines on this graph are F1 as a function of how much human labeling effort is there. And they are examples of surfacing positives with K and N. They're examples of deep label propagation, a bunch of the stuff from the recent literature. And these simple ideas of just using the human for the hard stuff, using the machine for the easy stuff, flooding the system with a bunch of machine labeled negatives is getting this red curve to be, significantly better in terms of what F1 score you can achieve at a certain budget than some of these fairly strong baselines. So this is some work that I'm happy to talk about or push you over to Ravi and Smith Hall to talk more about as well. Now, we're also doing a number of other things. Like, for example, we are trying to use the machine in active techniques, but I come from a non-machine learning background, and I have mined for data in data sets well before I knew anything about deep networks. And so many of the actions or events that we are looking for are things that are human behaviors or well-structured things. Like, for example, finding interviews in TV news. And if I describe to you what an interview looks like, I'd actually be able to do that in words. I'd be able to say, well, usually there's this 2-person or 3-person layout on screen. There's a host, there's a subject, and usually the cinematography flips back and forth between those two or shows both of them on screen. So we have other projects. We have another system here, which is called Recall, which says, don't worry about any of this learning stuff at all. Just use human knowledge to programmatically define what they are looking for. So we assume that we have all of these low-level labels on the data set that can be pre-computed. So that unlabeled data set is unlabeled with respect to the label or activity that I want. It's not labeled for interviews. But it can be labeled, like I showed you earlier in the talk, with all the faces or all the objects or a scene description. And so then with all of this primitive symbolic information, I can treat this like a databases problem. So I can just start authoring queries to say, look, I'm looking for all patterns where, for example, Bernie Sanders and Rachel Maddow appear on screen at the same time. Or I'm looking for temporal relations between these two using something like the Allen interval algebra to say I'm looking for situations where Bernie appears just before Rachel. So we've come up with some simple query language definitions that we often use to write simple test predicates, like I think an interview is this symbolic pattern. And this is stuff that can run on the data set in milliseconds to seconds. You get feedback and you tune your queries just like any other conventional programming system. Okay. And what we found is a reasonable programming model for this borrows a whole bunch of ideas from the multimedia database community. Much of that community existed at CMU well before I was there. And so some very simple abstractions, like thinking about a label, a face detection, as a spatiotemporal volume in a video. Thinking about a word in the transcript as having a spatial extent, and then being able to generate hierarchies of those. Like a track is just a sequence of face detections of the same person. An interview is a sequence of Bernie followed by Jake Tapper followed by Bernie. So we just write these simple programs that are based on spatiotemporal operators and joins. Like, for example, you might have a set of face detections A, you might have a set of another face detections A, and you can obviously join these in time or in space. And so without any learning at all, we are able to use these queries to generate usually reasonable precision, kind of low recall results in large data sets that really all we have as a prior is human intuition. So if you're interested in like what a cocktail party of of interviews on Fox and CNN and MSNBC might look like. Well, I've got the sound turned off, but this is what it looks like. So we're quite excited about any of these systems that allow the human to stay in the loop and have debug test cycles that are on the orders of seconds, much more like conventional programming. And this is very useful in curating, in writing heuristics for debugging and validation, as well as curating the data to get out of that bootstrapping phase so that more traditional machine learning techniques can take over. And then last, one of the things that I'm actually quite excited about is we're actually trying to put all of this together in a single interface. And let me, if I pop out of here, I think I can show that to you real quick. Sorry, let me, I think you should be able to see my screen. And it's amazing how fast you can compute with elastic computing resources these days. So we've built some systems now that we hope are in collaboration with folks that know a little bit about design, that we hope should make it very, very easy to go from an idea to at least a bootstrap label set in a couple of days. Like, for example, what you're looking at here is a clustered version of all of the Waymo data sets. So if you're interested in, like, for example, there's this cluster here, which looks to be rainy days. I can tag it rain, pop back up, train an SVM. I've already pre-tracked some stuff rain. Sample negatives according to some pre-trained embeddings. And in not too much time at all, I'm all of a sudden taking my second round of labeling the data. So I'll let this run for just a few seconds. I think our cluster is booting in the background. Give me 1 second. Yeah, and not too long at all, now I'm exploring Waymo with the top of the data set being all rainy things. And so we're getting to the point where we can take an idea, for example, in the Waymo data set, say, hey, today we're looking for green trash cans that have this logo on it. And somebody can get to tens of thousands of labels pretty quickly. And we're integrating these techniques like background splitting and this programmatic querying into the system, so we can iterate very quickly. If Satya is in the audience, this has strong echoes of Satya's old work on exploratory data mining with Diamond. So we take a lot of inspiration from that as well. And then last, I just want to bring this back to some of the systems topics that I feel a little bit more comfortable with. Is we are very interested in what can happen when we have one of these human experts, someone, an engineer, data analyst. You get the right interface in front of them, you get the right training techniques in front of them, and then you give them supercomputing scale compute on the back end while they're sitting down at the desk. So where we are going with this Forager interface that I showed you is we are trying to pursue an interactive human-in-the-loop data curation and model development process, where the #1 design principle is that humans are labeling and validating concurrently with training, and both sides of the fence. The human should see the latest results from the model almost every checkpoint or every epoch. The model should see the latest results from the labeler at the same time, and the system should be such that neither of the two ever go idle until the model has been verified. And so we've done a few things to try and, like, okay, how is the human gonna not wait while we're working on training, or we're working on large-scale inference to mine these needles in a haystack? So the systems folks in the audience are probably well aware of the trends in elastic computing these days. So it's not very hard to go grab several thousand CPUs from Amazon and get them literally in 20 seconds or so. So here's some experiments that we've been running as the back end to Forager, where we just go grab, whenever the user hits a button, we go grab thousands of cores. We pay about $1 or $2 a minute for those cores. But if you want to run a newly minted model with brute force inference over a large unlabeled data set, it's pretty easy to do that at extremely high throughput using cheapo cores in the cloud. So this plot here is the red line is the DGX1 in my lab. And to be fair, the code is not extremely well tuned up on that. So there's 8 high-end GPUs there. The blue lines are various versions of us using thousands of cloud CPUs to improve inference by about an order of magnitude or so over the DGX1 so that our users are never waiting. So we're very excited about building systems that just fundamentally, we start thinking about thousands of machines per user, instead of users per machine, which often is what we sometimes think about in computer science. And last, everything that we tend to work on, whether it's my tennis data set, some of the other sports data sets, or even the TV news data set, it's not internet images. There's an enormous amount of structure and redundancy in the data set. And so it'd be very remiss to, going forward, to not try and get massive amounts of performance out of specialization to the data distribution that we're working on. So again, here's another data set, a popular street cam data set. And even in this situation where the camera is stationary and not moving, distribution shift is non-trivial. So here, every row are different images from the same stationary camera on the same location, just different days or different weather patterns. Here's an example from my tennis data set at Wimbledon over the course of 3.5 hours, or I guess this match was probably 5.5 hours. The images look pretty different. So one thing we did a couple of years ago is we were like, shoot, is there any way that we could specialize these models for the task to get much cheaper? And we did some experiments where we trained on all the data and then tested on some, tomorrow's data. And then we did some experiments where we trained on today's data and tested on tomorrow's data. And then we did some experiments where we trained really quickly on tomorrow morning's data and tested on tomorrow, not after it. And to our surprise, it was always the last one, the most recent data, obviously in hindsight, was the data set that was actually the best. So we did some work where we just said, screw this idea of a data set at all. The world is always changing, but it's never changing that fast. So why don't we just start thinking about not worrying so hard to curate the training set that you need perfect for a data set? Why don't we just take things as they come? And so if you're fast enough where you can train online, you don't have to worry about, if you've picked the right data for training. So we did this for semantic segmentation, and outside of my group, some follow-on work by Deva is applying these ideas to object detection. But for semantic segmentation, our idea was, we called it JITNet, stemming from just-in-time compilation, but we just have a very tiny DNN that is engineered to be so tiny that we can train it on the fly. And so that tiny little DNN is just supervised by a big expensive DNN periodically, and just bumping the weights of that DNN is enough to keep it up to date, and so it's producing accurate results. So here are some examples. On the left, you see kind of classic mask RCNN at about 3 frames per second. On the right, you see the output of this tiny little JITNet, including the cost of running mask RCNN periodically for supervision and including the cost of training it on the fly, ends up generating segmentations that are roughly comparable. Okay. And one thing to note is you'll see the lady in blue walk in front of the judge. Her segmentation falls apart because we've never seen that situation before. After about 6 seconds of wall clock time, the JITNet has actually repaired itself based on supervision. And here's another example with a moving camera. This is not specific to stationary cameras. Here's another example in egocentric, where there's huge amounts of motion. Notice that the camera is about to swing to the left. We haven't seen anything like this. The segmentation on the right is kind of busted. And with only a few frames of supervision, it can refit to what it's seeing very quickly. So like this, I sort of feel as a towards a vision kind of talk. But the area where we work in every day, or where we want machine learning tools, is we want machine learning tools for subject matter experts that know a lot about what they're doing, not paid Turkers or anything like that. Subject matter experts can go from an idea to a model that they have some trust in an interactive, exploratory process, from the morning when they sit down at their desk to when they go home in the afternoon. And there are many things that we haven't touched on. I didn't say anything today about data augmentation. I didn't say anything about even faster indexing or the system side, too much about the system side of this. I certainly didn't say anything about model validation. And some work that's ongoing right now is about how can we more efficiently choose samples to validate models? Because if you're not labeling a lot of data to train your model, you also can't label a lot of data to validate that model. Okay, so I'll stop there. I just wanted to say that this is work in collaboration with a bunch of folks at Stanford, but also a bunch of folks at CMU and Google. So thanks for letting me talk to you. And I think I'm going to stop the talk here. I have one more thing that I'd like to run by people maybe after the talk is over, because we have some results in another area that I think might be broadly useful to reinforcement learning folks. And maybe I'll jump to the final slide. The final slide is we've redesigned renderers to generate experience for simulated environments in machine learning. And by taking computer graphics ideas and just doing things right, we have a paper at iClear this year that just is able to render, infer, train loops in RL simulations at an order of 13,000 frames per second on big Gibson meshes. And we've since made that 5 or 6 times faster. So we're now operating in a regime where there's 26 years of human experience in a day per GPU. And we're really interested if anybody could use that for reinforcement learning projects that don't require heavy physical simulation, but require heavy perception. So I'll stop there. Sorry for the one plug. But thanks a lot.
All right. Thank you, Kayvon. Is there any question from the audience?
Hi, Professor. I have a question regarding the bootstrapping. So, can you hear me?
Yes, yeah, I can hear. Sorry, I can't see you, but I can hear you right now.
Yeah. So my question is: so can we use some few-shot learning method instead of trying to augment the data set to bootstrap a classifier or a detector, like just with a few shots of labeled data?
Well, we are operating in a so-called few-shot regime, right? Because I'm starting with, in the example that I gave you, I'm starting with 5 shots.
Yes.
And what we have found, and this is a very unscientific answer, because like I said, I feel very new in this space. But what we found is when we're doing few-shot stuff, if I go back to, hold on, give me 1 second. What we have found is the literature that we've read and tried in a few-shot scenario is run on data sets where the categories that you are trying to discriminate are extremely widely separated. And so from an example like this, where you're trying to figure out what this lizard is and differentiate it from this lizard in the second column, or you're trying to differentiate a Federer slice backhand from a Federer slice forehand, or we have some work going on right now in Olympic sports where we're trying to differentiate like a toe loop from a Salchow in figure skating. We have just found that kind of like how the imbalance data, when you took it out of kind of the very pristine, curated academic data set regime, really started to fall down. We're finding that a lot of that low stat stuff is falling down. So I really, one of the things that I would love to see happen is for all of us to start developing and testing on some data sets that are kind of constantly evolving in real world. Like I get footage from MSNBC every single day. And it would be great to sort of just start running competitions and experiments, which is, okay, somebody's going to think of a category today. It's brand new data. It's really fine grained. Everybody go at it and submit their model by the afternoon. Those are the types of sort of competitions that I'd love to see run.
Okay, I see. Thank you.
Yeah. Mm-hmm.
I think there's also a question from Mark. Mark, do you want to just ask directly?
Chat? Yeah.
Sure. So that was really cool, especially that little piece at the end there. I was wondering, with the small DNA and occasionally supervised by a big one, is there sort of an optimal or advantageous amount of time or cycles that the small one needs to be supervised or checked in on?
If I make an analogy to video compression, like if the world changes rapidly, you burn more bits, right? And it's the same thing kind of here. If the world is changing rapidly, you're going to burn more compute, because you're going to have to burn more compute to generate more supervision and to do more training in order to keep up. So this was the, this is the big thing that Dave Anderson was beating Ravi on, who did that work, in his thesis proposal at CMU last year, which was like, hey, like this sounds a lot like an adaptive sampling situation that we're very good at in networking with packet backoff and stuff like that. So what we use currently is a fairly, use the first thing that comes to mind, is we use an adaptive sampling with backoff to ratchet up the rate at which we are training if we think we're getting out of whack or we're falling behind. And then we back off when the world is changing very slowly, like if this was a stationary camera and nothing's going by the camera. So that's the technique that we use. Dave actually gave us a bunch of tips on better ways to do this type of sampling from the networking community. Did that make sense?
Yep.
Was that fair? Okay.
That's a great answer.
But I think the analogy would be, look, like if I'm trying to take video on a fast moving camera of a highly textured surface, you're going to burn more bits, or it's not going to look as good. Yeah. And now it's just compute. Another question people often ask is how long, right? Like if you turn around the corner, are you're willing to run into the first thing, but you'll be able to figure out not to run into the second thing. So there are obviously situations where this would maybe not be a good idea, and people immediately start recommending memory-based systems where we keep old frames from the past around. And that's actually proven to be harder than it seems in terms of how to make decisions on how to balance forgetting and sort of responsiveness of the training against remembering old things. And just kind of like what some of the fast robotics people with optical flow kind of find is, in general, like if you have to remember, you have to be really clever. If you can just go really fast and update yourself very quickly, you don't have to be clever. You just need to respond really quickly. And often it seems like the latter is a good strategy, which is kind of the anti-generalization argument.
Hi, Kayvon. This is Babu Pillai. Great talk.
Oh, hey, Babu. How are you?
Good. I was wondering, you mentioned some work with Deva on kind of human-in-the-loop labeling for very, very imbalanced and very low incidence positives in a very large negative data set. I was curious, was this primarily referring to that Eureka and Delphi work that Dave was involved in, or is this?
I don't know. Those sound like grants, so I have no clue. The work I'm referring to is a paper called Background Splitting. Deva and I worked on it. Ravi Malapulli at CMU, and that work is going to appear in CAPR coming out this year.
Okay, great. Thanks.
Yeah, it's background splitting. I don't think we haven't. We're very slow to archive things, so we should archive some of this stuff.
Sure.
Yeah.
Hi, Kayvon. I'm Shilpa. I have a doubt. I have a question on the training you did for the background splitting.
Okay.
Like you're doing the multitask training, and you said you're not using the model trained with the ImageNet pseudo labels. You mean we are not, or we are? We are definitely using the model. The model is trained with basically 2 heads and 2 losses. One of the heads is the traditional supervised learning head of the task we care about. And then the second head in a classic multitask setup is that second head is trying to mimic the output of some existing model. So if we just use pseudo label without the right model for training, would it still give a good result?
When you're saying without the right model for your training, are you saying that is our model architecture important here?
Yes.
Is that, yeah, okay. I don't think so. Our model architecture is just off-the-shelf ResNet. We did 0 innovation in that at all.
Okay. No, my question was, if you just trained for the fine-grained, but gave pseudo labels from ImageNet without training the network.
Oh, I see. So you're saying, okay, I think I understand your question. Your question is, why don't I just have a single classification head that augmented the binary classification task that I care about with 1,000 additional categories and just do 1,000 plus 1 Is that right?
Yes.
Okay. Yeah, so we tried that as well. And it creates some complications. So first of all, actually, it just didn't work as well. And I actually would probably defer to the lead student on this, Ravi Molapuli, who's CS at CMU right now to get to the details. But one of the biggest things is actually just practicality. I've learned an N+1 classification head now. And I really wanted a binary classification head.
Okay.
So now I need to not use exactly the same model at runtime. Mm-hmm. And what I like about the multitask setup is you literally just turn on, you just get rid of that second head and you only take the output from the primary head. Oh, and like the only parameter in the system is the loss that you want, how you want to weight the two losses, the aux loss against the main task loss. And so it's a much easier to adjust parameter.
Thank you, Kayvon. It was a great talk.
I think there's a question from Benedict. Do you want to go ahead?
Yeah, thank you. Great talk, Kayvon. I have a question regarding this example that you had with the interviews and the face detection algorithm.
Yeah, right.
That was a really great example of having domain primitives that can help you define these rules that you were talking about.
Yeah.
Is that an example that you do see quite frequently and for static data sets as well? Or is this basically having a library of these primitives that you can write great rules over? Is that something that applies to a broader set of tasks that you see in your work? Or is this just a really great example?
Well, I think it depends on the data set. Like,
yeah.
If we are evaluating situations that were either created by humans or involve humans, there tends to be a lot of human structure. Like, for example, one thing that I'm really interested in doing is using this rule-based system to see how far we can go in analyzing professional sports data. So if we have, I'd like to use machine vision to do the super low, like to generate the primitives. So for example, fine grain action recognition might give me forehands, backhands, slices, or in basketball, pick and roll with Steph Curry and Draymond Green or something like that. But I don't think I want to learn their composition. Like once we get up the stack a little bit, I have a pretty good idea where I am like the domain expert or the analyst. Like if you give me all of the jump shots or you give me all of the basic actions in basketball and I want to find a particular play, I feel like I should just be describing that play with some rules because the coaches think about it as rules. The analysts think about it as a set of rules. So my hypothesis here is that it makes very little sense to throw out that structure, that knowledge, and try and relearn it. And our tennis stuff with the Roger Federer, like people saw it and said, "Oh, that's deep fakes." What model did you use to generate those behaviors? And actually, there wasn't anything at all. Like we have a very simple hand-authored state machine. It's really a computer graphics project. It's not a machine learning project. That controls the character because I know a lot about tennis. I don't need the machine to learn about the fundamentals of tennis from watching a lot of video. It's an interesting academic thing, but from an engineering standpoint, a lot of those rules I can just write down. But the rules I can't write down are like, what is a smirk? Or like differentiating a slice from a topspin is more like, look, just look at the motion vectors and figure that out with pattern analysis. So as it gets lower and lower level, I cannot symbolically do anything. As it gets higher and higher level, I feel like there's more and more opportunities for rule-based systems to layer on top. But that's just a hypothesis. Like, I'm not going to differentiate night from day in the Waymo data via rules or heuristics. Learned classifiers will do just fine. But if I wanted to say I'm looking for a bus at night right before I see a police car, that's not something I want to specify by example.
Thank you.
Yeah, and Katarina, you have a question?
Yes, thank you. Hi, Kayvon.
Hey,
A great talk. I have a question regarding the semantic segmentation example that you showed. And I was wondering how exactly do you get the ground truth to train the segmentation online? So is it that you can train your model so quickly and so efficiently to
the ground truth in this case is a very expensive model that we quote unquote trust. So you know, I only gave that project 2 minutes, so we didn't get into the details. But one of the biggest challenges in that project is the big assumption is that there is a model that exists to provide supervision that you trust. So that could be an expensive learned model. That could be a model that you smooth over with heuristics. But we are distilling the output of that teacher into the tiny model. And if you have a teacher that is just junk, this is not going to work very well. So one of the interesting challenges going forward is how can you use this process, maybe a little bit of yin and yang between the teacher and the student, to actually improve the teacher as well, because the teacher, being this very small, compact model that has fewer parameters and is, you know, harder to overfit, actually outperforms the teacher in many situations, because it's just extremely specialized with a compact representation to the data at hand. And sometimes that mask-RCN model bounces around a little bit. So there's a significant issue of, if you can't get supervision, you're screwed. But that's where all these other things, like the slide I have on right now, we're hoping that a combination of forms of supervision might be helpful.
Okay, thank you.
Yeah, but in the example, the short answer to your question is that in this case, like mask-RCN, we treat as a ground truth standard for those data sets.
Okay, thank you. If I may ask, just as a follow-up, so I've been studying a bit about this topic as well, and I was wondering what are the relations to the Snorkel AI, which I believe is a tool developed.
Yeah. So Chris Ray is on the collaborator list here, and I'm really having a lot of fun learning from Chris. So, you know, weak supervision, and like, so you can think about these rule-based systems that I'm describing here as one way to impart weak supervision into the system. So Chris views these rule-based things as labeling functions. And to your question of how do you generate that supervision, we're really interested in combining various sources to generate a teacher that's more trustworthy. Absolutely. Absolutely.
Okay, cool.
I definitely, from interacting with Chris, I definitely view that, you know, the data that we label, but with human eyes, is going to largely be for the little bit of labeling for bootstrapping the process, and then most of the labeling that I envision us doing in the future is all for validation. So all the training data is going to be weakly supervised or very sparsely supervised with humans. And then every day, all my human eyes are going to need to go into validating whether or not the distribution shift that occurs has mucked with my accuracy.
Okay, thanks. It makes sense.
Hitesh, do you have a question?
Yes. Can you hear me?
Yes.
Yeah. Thanks, Professor, for the great talk. I think a couple of questions related to the previous answer. I think I want to understand your thoughts on, I think you briefly mentioned how to choose the right validation data set as the world is evolving. How do we evaluate our models on? And on a related note is basically why I want to know that is, like, we want to know that as the world is changing, our model is behaving purely, so it needs to be, retrained or something.
That to me seems to be like the biggest problem right now. And so we are working very aggressively right now on one of our first papers on validation. And you should talk to, well, there's a student of mine that's Faye Palms, who is one that's leading that effort. And actually we're basically trying to do all of our validation stochastically with various forms of importance sampling now. So we think that statistical or probabilistic validation is actually the best way to do things in this constantly changing environment. I'm gonna be very hesitant to say anything, not to protect research results, but this is one of those projects where every 48 hours our opinions change. And so go talk to some of my students in about 2 weeks in terms of where do we fall in terms of this. But I agree with you at a high level that trying to figure out how to validate these things in a constantly changing data landscape seems to be the name of the game. Like, for example, in our TV news data set, I would love to allow anybody in the world to create a model on the fly and be able to report out like I have a journalist at the New York Times say, it appears that, you know, masks appear on CNN twice as much as they appear on Fox News or something like that. But I have no idea how to put those tools in someone's hands in a manner that and give them a prescription on how to trust it.
Got it. Yeah.
Ironically, probably the worst, like there's always talk about how face detection and various forms of gender classification don't work nearly as well on female presenting individuals. It actually turns out that one of the most poorly detected persons in our, or not detected, but classified persons in our data set is actually Donald Trump. Men with blonde hair actually throws things off big time. It's kind of funny. Like if you go check Amazon recognition or those services, where do they mess up the most? They actually are pretty bad on Trump.
Great, thanks a lot. Yep.
Mm-hmm.
Any other questions or comments? Okay, I think we're kind of running out of time. So let's thank Kayvon again for the amazing talk. It's hard to clap in the virtual setting.
No worries. Thanks. Good to at least hear everybody again. Good to at least hear everybody again.
Yeah, I think people clap in the participant list.
we should use we should use OEA for this. Yeah.
All right. Well, as a reminder, we're meeting at the same time again next week. So thank you, everyone, and especially Kayvon for attending the seminar today.
Take care, everybody.
Yeah.
Stay safe. Stay safe.